All right, so here we are, part 2 of Enzymes and Kinetics. So enzymes are catalysts. Enzymes are specific and can be regulated and are essential for the function of survival of cells. Enzymes increase the rate of reaction by stabilizing the transition state. So essentially what an enzyme does is it gets to, well, stabilizes this, but more than anything else, it takes the delta G double dagger and lowers it. They do not change the free energy, which the free energy is the difference between our reactant and our product, which is behind my head, but essentially it's right there, but on this line. What they're doing is they're changing the difference between the transition state and the reactants and products. So we're not changing the difference in energy of the reactants and the products. Those two stay the same. So the starting point and the end point remain the same, but instead it's this transition state free energy that changes. So an energy diagram looks a little bit like this. So what we have here is an energy diagram of C plus AB, and what we result in, our product, is Ca plus B. Energy diagrams show the changes in energy that occur in going from reactants to products. What y'all need to know, what I want y'all to know about, is this activation region right here, the heat of the reaction, which is right here, our transition state energy, which is right up here, and the reaction coordinate. So your reaction coordinate shows basically the pathway that the pathway of our free energy change. So we start, we go up, and then we drop down lower than the products. If we drop down higher than the products, well, then we've created something that's less stable. So that's not ultimately going to be a good thing. Now, active sites. Most enzymes are globular proteins that contain an active site. Active site definition, the binding surface where chemistry actually takes place. We've already talked a little bit about this because we talked about the amino acids that were in the active site, but the amino acids at the active site interact with the substrate and can participate in the chemistry. Now, substrates that bind at the active site, or substrates bind at the active site, chemistry occurs, and our products are released. So there are two models for how a substrate interacts with the active site. One model is known as the lock and key mechanism, meaning that the active site has a particular shape and the substrate has a complementary shape. This is a very highly specific model, just like how a lock has a very highly specific and highly detailed place for where a unique and highly specific key fits. The next model is an induced fit model, in which case the enzyme is fairly flexible and can contort itself to fit a kind of a range of different substrates. This is much lower in specificity, but it basically relies on the enzyme, the enzyme being able to change a little bit in order to match the shape of the substrate. Now, conjugated proteins. Many enzymes are conjugated proteins and require non-protein components, cofactors. We've already talked about those. There's a unique terminology for a enzyme bound to a cofactor, and that is a holoenzyme. An apoenzyme is the enzyme without its cofactor bound, whether that cofactor is an organic molecule or a metal ion. It doesn't really matter too much there. Now, classifications of enzymes. There are currently a total of 7 major classes, but in most textbooks you're only going to find 6 of these classes, and so we're only going to focus on those 6. The 6 different classes are oxidoreductase. So an oxidoreductase is an enzyme that carries out redox reactions. There you go. A transferase is a type of enzyme that transfers groups. Now, this number up front here is unique for what's known as the EC, enzyme classification numbering system. So every single transferase will have a unique identifier that starts with 2. Every single oxidoreductase will have a unique identifier that starts with 1. So group number 3 are your hydrolases. These are enzymes that cleave bonds with the help of water. They catalyze hydrolysis reactions. Lyases, these are enzymes that involve a double bond, and they either, they're going to be adding a double bond or they're going to be creating a double bond. sorry, adding or removing a double bond. Our last two class of enzymes are isomerases and ligases. Isomerases, well, they're just going to isomerize a molecule, and a ligase is going to be a type of enzyme that creates a bond between two different molecules. Now, your examples, or some examples, are all detailed here. An example of an oxidoreductase would be an enzyme like alcohol dehydrogenase, which our substrates are right here, where we're taking CH3CH2 OH and producing this guy right here. Transferase, where you take glucose and you make glucose 6-phosphate by transferring a phosphate group from ATP onto that glucose. Chymotrypsin, which takes a polypeptide and water and makes two individual peptides or more peptides. A lyase takes pyruvate and decarboxylates it, elimination of our double bond there. So we're removing this right here from our substrate molecule. An isomerase D-alanine is interconverted to L-alanine with the help of this enzyme, and a ligase, well, it's not displayed here, but essentially what we're doing is we're making a molecule known as phosphoenolpyruvate by taking this pyruvate and adding a CO2, and we're using ATP in order to do that. So I'm sorry, we're not making phosphoenolpyruvate, but rather we are making oxaloacetate, which oxaloacetate looks like such. I gotta get my pen back. Okay. We're getting rid of that 3, 2, C, O minus. That's what oxaloacetate, or OAA, is like. Now, Michaelis-Menten kinetics are our way of measuring how fast a reaction goes. So this model was originally proposed in 1913, and what it relies upon is this ES, or enzyme substrate complex. This is the intermediate that's formed at the transition state. So the Michaelis-Menten equation is displayed here, where we're relating the enzyme's affinity for our substrate, or our KM, to substrate concentration, and that substrate concentration multiplied by the maximum velocity of our enzyme. Okay, so what I really want you to take away from this is I want you to understand this equation, but I want you to understand it in the context of what does a graph look like. So exponential determinations of Km and Vmax are made using what are known as Lineweaver-Burk plots, which are double reciprocal plots. So it takes the exact same Michaelis-Menten equation and makes it an inverse, or a double reciprocal plot. So this right here is a Michaelis-Menten plot. Our y-axis is our initial velocity, and that's graphed against our substrate concentration. Now, what you notice early on here is that as your substrate concentration goes up, so too does your velocity. And you can continue that on, but one of the things that I want you to take away from this is not a linear plot. So the line that I drew there is a linear representation, or a linear graph. Instead, what we see here is as our substrate concentration increases, at some point, we see like a diminishing marginal return, in that our velocity begins to actually kind of plateau and taper off. It ultimately kind of stops. So the increase in substrate concentration will not be indefinite. You cannot continue increasing the substrate concentration. Your enzyme velocity just keeps going up and up and up. And at some point, it's going to basically plateau. So our Lineweaver-Burk plot is shown here, where we have on our y-axis 1 over our velocity versus our x-axis 1 over our substrate concentration. Now, what we see with that is ultimately our Km and our Vmax, which again, our Km is our substrate affinity, and our Vmax is our enzyme's maximum velocity. So where this ultimately plays out whenever we graph this is our y-axis shows, or our y-intercept shows us our 1 over our Vmax. And our x-axis, which this would be a negative number, that's going to show us negative x is equal to negative 1 over Km. So ultimately, when you take the Lineweaver-Burk plot, or sorry, our Michaelis-Menten plot, which is right like this is going to be our Vmax. We can plot our Km because our Km, in addition to being a measure of affinity for our substrate, it's also equal to the concentration where our Vmax is divided by 2. So what I do is, in order to predict what my Km is, well, I see this area where my substrate concentration plateaus, and that's my Vmax. So I'm going to draw that across. And then I'll say, okay, what's my Vmax divided by 2 on my y-axis? Well, it's about right there. Then draw a line, and I say, okay, well, here is my Km, because my Km is equal to my substrate concentration where my Vmax is divided by 2. Now, that is the nuts and bolts of how an enzyme and a substrate react to catalyze a reaction in ways that you can quantify an enzyme's reaction. Now, what you can also do is look at how a enzyme's reaction can be inhibited. And enzymes activity can be reduced by certain molecules called inhibitors. Now, these inhibitors can be reversible or irreversible. Now, irreversible inhibitors are also known as inactivators. Covalently modified enzymes, they covalently modify enzymes. Therefore, the enzyme is is basically not functional. It's irreversible. It can no longer carry out its reaction. Lead, for instance, can outcompete calcium in a calcium-dependent enzyme and basically render that enzyme non-functional, inactivate that enzyme completely, which is one of the reasons that lead poisoning is so hazardous, because it takes the place of calcium. Because if you think about lead, it's going to form a 2+ ion, and calcium is also a 2+ ion. Well, lead is similar in shape, but what it's able to do is insert itself where calcium was, and basically occupy that space and prevent the reaction from moving forward. Reversible inhibitors are where I'm going to focus most of my time. There are 3 types of reversible inhibitors. They are competitive, uncompetitive, and non-competitive. And they all do different things. One, a competitive inhibitor competes. It's going to compete for the free enzyme against the inhibitor. A competitive inhibitor will form an EI complex instead of the ES complex. So the way that I always like to think about this is E plus S yields ES. That's an ideal situation. Well, a competitive inhibitor will present itself right here, and it will take the place of that free substrate and instead produce the EI complex. So this complex forms rather than that. Okay, now you can basically outcompete that inhibitor by adding more S, by increasing the substrate concentration. Now, what that means is that you are increasing. A competitive inhibitor requires an increase in Km. So you have to add more and more substrate because the enzyme has lost its affinity for the natural substrate because the inhibitor is there. Now, a competitive inhibitor does nothing to change the maximum velocity of a reaction. So with respect to our 2 kinetic parameters, Km and Vmax, a competitive inhibitor does nothing to the Vmax. What does it do to the Km? It causes it to go up. It causes the affinity causes the enzyme's affinity for the substrate to go down because the Km goes up. Those 2 things you got to keep straight. If the Km goes up, the affinity goes down. If the Km goes down, the affinity goes up. So you could kind of think about it as Km going down. Now the enzyme has a higher affinity. It's happier. It doesn't take as much to get to It doesn't take as much of the substrate to kind of be, I guess, content. Now, a non-competitive inhibitor. A non-competitive inhibitor is different because of the fact that E plus S yields ES. Well, a non-competitive inhibitor, it's going to be able to bind to both the free enzyme, but also to this ES complex. So a non-competitive inhibitor could form this EI complex, or it could form the ESI complex. And what that is going to do is it's going to cause the Vmax to decrease. It's going to result in a Km remaining the same. Now, what's significant about this is that you could kind of think about this as what's better, a competitive inhibitor or a non-competitive inhibitor. Well, on one hand, a non-competitive inhibitor has a two-pronged approach to preventing the reaction from taking place. But, ultimately, when it comes to like a therapeutic or something like that, you have to compare them and, try different options. The last type of inhibitor is an uncompetitive inhibitor. And an uncompetitive inhibitor binds only to the ES complex. So E plus S, that can take place, no problem. It's going to form the ES complex. The uncompetitive inhibitor binds to the ES, forming the ESI complex. So what this is going to do is it's going to cause both the Vmax and the Km to both go down. Now, what that is going to mean is it's effectively going to cause the enzyme's affinity for the substrate to go up. Why is that? Well, that seems a little bit backwards, but think about what's happening. You have I'm going to erase all this up here so I can have a little bit more space to draw. You have your free enzyme and your ES complex. Now the inhibitor is going to come over here. It's going to form this ESI complex. So let's say that you started with 100 copies of the free enzyme. What's going to happen? Well, slowly but surely, the 100 copies of the enzyme, they're going to basically vanish because a number of them are going to be captured there as a part of the ESI complex. So slowly but surely, the pool of enzyme goes down. And so what that means is that if there was a saturating amount of your substrate for 100 copies of the enzyme, now you're down to 50 copies of the enzyme after one round because 50 of them are wrapped up as a part of this ESI complex. So that means you have fewer numbers of the free enzyme fighting over the substrate, which is why your enzyme's affinity for the substrate increases. So the Km going down causes the enzyme's affinity for the substrate to go up. Okay. So at the end of the day, though, an uncompetitive inhibitor causes both the Vmax and the Km to both go down. Now, here's a display of basically what I just talked about. We have our competitive inhibitor right here. We have our non-competitive inhibitor right here, and we have our uncompetitive right here. So a competitive inhibitor only binds to the free enzyme. A non-competitive inhibitor could bind to the free enzyme, or it can bind to the ES complex, forming the EI and or the EIS complex. An uncompetitive inhibitor is only going to form this middle complex, this ESI complex. Now, what does that look like from a standpoint of the different graphs? And okay, so these two lines in an uncompetitive inhibitor, I want to start here just because my head's blocking them, they're going to be parallel. So no inhibitor, inhibitor. So the slope of this line does not change. Okay. And you guys have the PowerPoint so you can look at this graph independent of my face being there. Now let's go back to a competitive inhibitor. Y-intercept does not change. X-intercept changes. Our slope goes up. Now, a non-competitive inhibitor, our Km is unchanged. Our Vmax is decreased, so our overall enzyme is going slower. What this is going to do is cause our slope to go up as well. So these are Lineweaver-Burk plots, or double reciprocal plots, and then here are your Michaelis-Menten plots. What's going to happen in the presence of a competitive inhibitor? Well, we're going to ultimately get to our maximum velocity, our endpoint, but it's going to take a higher concentration of our substrate. Non-competitive inhibitor. Well, the line for the graph basically looks the same, but it's almost like it's been scaled down at every point. An uncompetitive inhibitor, well, what we're going to see is our destination is going to be lower, but the kind of shape of it's going to change a little bit because it's going to get a little bit steeper initially, but then it's going to plateau out. So that's basically what you need to know about these different graphs. Understand how an inhibitor and an enzyme interact with one another in the presence or in the absence of a substrate. What's going to happen? What different models are formed in this ES and ESI complex? So I want you to understand how Km and Vmax change based on competitive, non-competitive, or uncompetitive inhibitors. I want you to also understand, what is the enzyme doing? Is the enzyme binding to the free inhibitor? Is the enzyme binding to the free substrate? What's going on there? Or not to the free substrate, I'm sorry. Is the enzyme binding to the free inhibitor? Is it binding to the is it binding in combination with the substrate and the inhibitor? I want you to understand those parts of kind of this. So I hope this was helpful, and that wraps up our discussion of enzymes. All right, have a good one.